Good afternoon, folks. Thank you for coming to, looks like the first breakout session after lunch for all of you. My name is Dougal Ballantyne. I'm a solutions architect with Amazon Web Services. I focus on high-performance computing, which is kind of my passion as well. One of the fun things about high-performance computing is it places a lot of requirements on the AWS platform, and so I spend a lot of my time working with customers trying to get the most performance out of EC2 and EBS. And so today I'm going to try and take some time to walk our way through the EBS service, Elastic Block Store, and then also talk about some of the characteristics and component choices you need to make to optimize your platform for performance. So what we're going to cover today, we're going to do an overview of EBS. Now, EBS is kind of a constantly changing thing. It's a service. And so therefore, every time we do this presentation, I have to update it and add some more content. So we announce larger and faster volumes at reInvent, and larger and faster volumes are now part of the service. So for folks who haven't caught up with all the changes, we'll talk through that as well. We'll spend quite a long time talking about performance and the different aspects of EBS and EC2 that impact performance, so you can actually understand what choices you need to make when you're designing for performance or you have a performance goal you want to achieve. We'll talk about encryption. Encryption in EBS has become easier and easier as we go. We have third-party solutions that you're able to put on top of EBS volumes, but today we have the service KMS where you can easily just say, I want an encrypted volume, and it's a checkbox, or I want an encrypted volume, and I want to use a master key I've created with auditing in CloudTrail. And then we're actually going to leave some time for Q&A today. I'll do my best to see if we can leave time for about 10 minutes of Q&A at the end. So let's start with an overview of EBS. So for most builders, for most people getting started on AWS, it's get in and go. You create an EC2 instance, you attach a volume, you mount the volume when you launch your instance, you put some data on it, and that's about as far as you need to go in your understanding of EBS. And for a lot of customers, a lot of people building solutions on AWS today, that works great. But what I want to take time today is explain exactly how EBS capabilities function, what they're doing, so when you're designing an application that has performance goals, maybe you're designing a database that needs to deliver a certain amount of steady-state IOPS, or you have an application maybe doing a file share, and you need to have a certain amount of throughput from that. You know how to get that throughput consistently and the right way on top of EC2 and EBS. So in normal hard drive. So I've been working in storage for about 15 years now. I've committed to memory the rotational speed of most SATA and SAS drives. I've worked on 7,200 RPM, 10K, 15K. The average read and write latencies these drives deliver. And then you use that data to work out the right RAID array to build underneath your database. You know that when you put a RAID 5 together, you're going to give up some of your IOPS. You know that RAID 10 is going to give you the most performance, but you lose half your storage. All of this stuff is committed to memory to enable me to build a great solution. However, EBS is not a bunch of hard drives. And this is really important to understand that EBS is not just a hard drive that you plug into the back of your EC2 instance and you use. EBS is a service. And because it's a service, it's going to operate differently than your average hard drive. It comes with added benefits. There's extra features, things we're going to talk about like burst buckets you just don't get with a standard SSD plugged into your machine. So what is EBS? Network-attached block storage. So it's not part of your EC2 instance. It's separate from the EC2 instance. It's a totally separate service that you're actually consuming block storage from. It's designed for 5 nines of availability. 5 nines of availability is kind of crazy in storage. So it's designed for 5 nines, and if we look at the last 12 months, the trailing performance, we exceed that. Okay, so it really delivers on its promise of 5 nines of availability. Attaches to EC2 in the same availability zone. This is important to understand. EBS is in your availability zone. It's a service that's independent to the availability zone. So that's what you get the availability from, and that 5 nines. It also has a capability to do point-in-time snapshots. Point-in-time snapshots are stored in S3. This increases your durability. So S3 has 11 nines of durability, which is just a staggering number. And so when you save your data to a snapshot, it's being copied out of the EBS service and stored in S3. So a couple more things about it. We have some pretty tough goals, which I just covered already. but they're for regional daily availability goals trailing through the year. And so it's a pretty phenomenal number. And we managed to get some stats we could share with you now. So today, when we're looking at it, we're creating over 1.5 million volumes per day in EBS. And that's a pretty staggering number of volumes that are being created. So before we get too far into understanding the service and what the service does, I want to set some definitions so we're all talking about the same things. And they're kind of important because a lot of these come back as to how you launch a volume and create a volume. You're going to need to know these things. So we start out with IOPS, input outputs per second. This is a number. Typically, it's associated with provisioned IOPS, a specific number you're dialing in. I want 2,000 IOPS. Or it's part of the burst bucket of GP2. Throughput, the amount of data we're moving backwards and forwards on the volume, so read-write operations to storage. Latency, how long does it take for an I/O to get from my EC2 instance to EBS and back again? And it's important because we're going to talk about the different performance consistencies and latencies. Capacity, it's pretty easy. How big is the volume? Can go all the way up to 16 terabytes on EBS today with larger and faster. So you can put a lot of data on one volume and easily manage it. So the operational burden of managing large amounts of data on top of an EC2 instance has significantly come down with the introduction of larger and faster. And then we have the block size, or the I/O size. And this is really important because we measure things in sizes of I/O. So your application is going to be working in a certain I/O size. Your file system has a block size. And then EBS is going to be measuring things in block sizes. So there's 3 volume types in EBS. We have EBS Magnetic, which was the first one that launched. It's been around for a long time. We then introduced provisioned IOPS so that customers who had very specific performance consistency requirements could choose the amount of IOPS they wanted and have that delivered within 3 nines of performance consistency. And then last year, we introduced GP2, General Purpose SSD. And General Purpose SSD enables customers to get SSD performance with a very simple pricing structure and consistent performance to 99, so 2 nines, and also burst buckets, which we'll dive into. A little takeaway, something I want you to really understand when we're looking at the volume types. When performance matters, when performance is one of the aspects of your application that's critical, use SSD. It doesn't mean there's not good use cases for magnetic, and we're going to talk about that, but when performance matters, use SSD. So some numbers or some data that applies to all of our SSD volumes. IOPS are measured up to 256 kilobytes. Now, it used to be that we measured those up to 16. And when we launched the GP2 volumes, the general purpose, we now measure all of our IOPS for SSD volumes up to 256K. So what that means is if in the past you were sending a 64K I/O down to a PIOPS volume, we would actually chop that up into 4 I/Os, and you would consume 4 IOPS from the provisioned IOPS you have in your volume. That today would equal 1. Another thing that's changed in the EBS service is we now do pretty aggressive I/O merging on your behalf. So even though we measure up to 256K, if you send down 2 16K I/Os and they happen to be sequential because that's how your file system is laid out or your data is laid out, and we see that, we'll do our best to put those together and consume 1 I/O of 32K, even though you sent 2 down, meaning you don't use all the I/Os you've provisioned, including the I/Os are in your burst bucket. It's designed for single-digit millisecond latency. It's designed for. So that means that you need to understand how to achieve that, and it's not something that will just turn up if you start running on top of it. We're going to talk about exactly how to achieve single-digit millisecond latency. And again, our availability, we're designed actually for 5 nines across all EBS volumes, not just on our SSD. So a deeper dive into exactly what GP2 is. So it's the new default volume type for EBS. What we mean by default volume type is when you go to the console today and you go and launch an EC2 instance and the volume is not GP2 for the boot volume, we'll pop up a little warning on the screen and say, hey, have you thought about using GP2? Would you like to make that the default? And I'll talk a little bit more about why we've done that, but you'll notice that GP2 is the default block device for all of the AMIs that Amazon Linux runs on. Almost all of the AMIs in the console for the quick launch, they're all GP2 based. Every volume in GP2, every single volume can burst up to 3,000 IOPS or go higher if the baseline performance allows it. And I'll talk about that in a second, what that means. So what that means is you can provision a 10 gigabyte volume and get 3,000 IOPS from it, or a 500 gigabyte volume, or a terabyte. And if we go higher than a terabyte, you'll get more baseline performance. And the throughput of the volumes is increased. So when larger and faster came on, the throughput has gone from 128 megabytes a second up to 160 megabytes a second. Now, it's kind of important to understand that throughput, megabytes a second, and IOPS are closely related, but they're two separate limits on the volume itself. So this is kind of a busy graphic, but it's important. This is something we shared when we launched Larger and Faster. And I'll take a moment to explain what we're trying to show you here. So in the yellow is your burst bucket. And I'm going to take a long time to explain that. So the burst bucket is the capability that GP2 provides for all volumes. However, the green line is your baseline performance, 3 IOPS per gigabyte. And so as you can see, as we start to pass over the terabyte volume size, and for the people who do a lot of graphs, they'll get very upset. None of this is to scale. So that people will be like, that doesn't work. And so none of this is to scale. It's for graphic illustration. And so if you look at it, you'll see as we start to pass the 1 terabyte volume size, the green line, our baseline performance, that exceeds 3,000 IOPS. So at that point, our baseline performance is higher than our burst performance, and so that's the highest amount of IOPS that volume is capable of delivering. And so you can see once we get up to about 3.3 terabytes, roughly, or 3-something terabytes, we're now up at 10,000 IOPS. And so at 10,000 IOPS, that's the maximum number of IOPS the GP2 volume can deliver. And so now you're just adding capacity as you go all the way up to 16. Can we save questions to the end? Is that okay? I'll happily answer the questions as we get to the end. So understanding what the GP2 burst bucket does. So the burst bucket, in my opinion, is a really unique quality that you just don't see in regular hard drives and regular storage. This is the ability for a volume to have more performance at certain points in time than it would typically have at other points, so the steady state versus burst state. So every single GP2 volume which is created, when you do create volume, those 1.5 million volume creates a day, when you do create volume, it comes with a 5.4 million IO credit bucket. So it's automatically ready to go with 5.4 million IOPS. It will always accumulate IOPS for every second at the rate of baseline performance. So if we have a 100 gigabyte volume, it's going to be accumulating IOPS at 300 IOPS per second. So it's always filling in at the top. And then you're going to use the IOPS at the bottom of the bucket at the rate that you drive your workload. So when people talk about burst buckets, or when people talk about burst, I think the analogy that comes to mind for me is a firework. Like it goes up and it goes bang and you're done. Burst is gone. It's like a couple of seconds. That's not really the reality with burst buckets on GP2. So we have a tiny percentage of customers who've actually emptied their burst bucket. It's 0.0 something. It's really tiny. Because it takes a long time to empty your bucket. So what we're graphing here is the size along the x-axis and the time it takes to empty the burst bucket if you run flat out at 3,000 IOPS per second. Okay? And so if I give you an example, a 500 gigabyte volume would take 60 minutes of sustained 3,000 IOPS constantly to empty that bucket. But that also makes the assumption that you're driving the IOs and we're not doing any IO merging. So that is 100% random. No IOs are matched up to get each other because we'd count that as 1 rather than 2. And you've driven it flat out. It will take 60 minutes to empty that bucket. It just doesn't happen. It takes a really long time. What we also show is that once you get past the 1 terabyte volume size, you can't empty the bucket because the bucket's only 3,000 and the volumes are capable of doing much more. So what does this really mean for real-life workloads? What has this done for you if you're launching an EC2 instance and choosing a GP2 volume? So a good example to illustrate this is the Windows boot volume. They're typically a 30 gigabyte volume for a Windows boot volume. So it's going to get that initial credit of 5.4 million. And it's going to be able to burst up to 3,000 IOPS for 30 minutes. Okay? It's pretty phenomenal, it can do that. And it's always going to be accumulating I/O while it's running. So if there's even a slight moment where it's not consuming all of those 3,000, which is hard, it's going to be building up more IOPS. So what it ultimately does is it substantially lowers the boot time for your instances. And so we did some testing comparing magnetic to GP2 for both Linux and Windows. And if you take a look at the Windows, it significantly drops. Now, we didn't change anything. This is not an update to Windows. Nothing changed in the AMI. The application is not re-architected. We simply chose a different volume type when we launched. And when you choose that different volume type, you get a faster boot time. Now, the impact on this for customers is pretty dramatic. We had customers who had auto-scaling groups who would actually over-provision their auto-scaling group in Windows because the boot time would take too long for the Windows instance to come up, and you want to react quickly with an auto-scaling. So they would over-provision 1 or 2 instances to sort of always be on the leading edge. You don't need to do that anymore with GB2. The boot time has come down, so you can now just add the instance quickly. Another example is database volumes. And so when you had magnetic, the other choice was provisioned IOPS. So for a database, the right choice would be provisioned IOPS. So you would choose a provisioned IOPS volume, a 1 terabyte volume, 4,000 IOPS. It would come in at $526 a month. But if you move over to GP2 today and just use a 1 terabyte GP2 volume, you'll be able to do that for $102. But you're going to lose some baseline performance. You're going to drop down from 4,000 to 3,000. Now, that might work for your application. That might make a lot of sense. But you can also do something really creative where you can grab 2 GP2 volumes. Remember, each volume has got 3,000 IOPS of burst. Stick 2 of them together, the dreaded RAID, which we've managed to get rid of for a lot of larger and faster, but it still makes sense here. And you'll actually get a baseline performance of 3,000 IOPS, but a burst to 6,000. So now you've got more performance than you had on your provisioned IOPS, but it's still $102. And so this makes a really big difference if you're building out databases that don't require the highest level of performance consistency, which PIOPS delivers. You can build them on GP2 and be substantially better than you were on magnetic. So some guidelines for sizing GP2. Like if you're going to be moving on to the GP2 EBS volumes, how do you size them? What is the right way to do it? Simply, for most applications, for most workloads, it's the size of volume you need. So if you need 100 gigabytes of storage, just provision 100 gigabytes. For databases or applications where you actually have an IOP baseline, some steady state that you need to maintain, you need to work out the size that will deliver that steady state of IOPS. And so, for example, if you need to deliver 300 IOPS, then you take 300, divide by 3, it's 100 gigabyte volume, and that would be the volume you can provision. Note that the I/O bucket is actually going to deliver a lot of performance. The burst bucket is going to deliver a lot of performance, so you don't need to size it for table loads or rebuilding indexes. It's what is the steady state of the database. Now, our EBS provisioned IOPS volumes, they're targeted at really high performance consistency. When we think about it internally, we would think about this as like a tier 1 database, and a database that if you were doing a select statement and it stalled for a second, that would be noticed. This is the type of workload that you'd want to run on top of provisioned IOPS. And so provisioned IOPS enables you to provision significantly higher IOPS, up to 20,000 IOPS, and significantly more throughput as well. But you can do it with a lot less storage. So the IOPS to gigabyte ratio is 30 IOPS per gigabyte, meaning you can provision in 4,000 IOPS in about 140-something gigabytes of storage. So it's very easy to do that on top of it. It's also designed for 3 nines of performance consistency, which is extremely consistent performance. So you know you're always going to get those IOPS within the time that you specify. Magnetic volumes, absolutely not to be forgotten. You can think of EBS magnetic volumes as nearline storage within the platform. When you need to have a lot of storage that needs to be there, you need to be able to access it. Maybe you have a POSIX requirement. You can't put it into S3 and lifecycle it to Glacier. The EBS magnetic storage is going to be the right choice for your platform. For types of file servers, for different solutions like that, exactly. The latency is going to vary, and the throughput is going to vary, and we'll highlight that in the summary sheet. So it's one of those areas where if performance is required, you really want to be focusing on you really want to be focusing on our SSD-backed volumes. So this is our summary or our cheat sheet. This is typically where everyone grabs their camera, takes a picture, but all of our slides will be on SlideShare, so you can download them and take a look at them offline. So you don't need to worry about taking pictures. But really the takeaway here is the fact that things like throughput per node, so 48,000 IOPS, that's an attribute of the EC2 instance, not of EBS, and that our latency numbers are consistent for SSD. And so you can use this to work out what kind of workloads might fit best for your volumes. So why did we make GP2 the default? Why have we made so much effort, and why have I spent so much time explaining about GP2? So first off, we're able to deliver a really high baseline of performance. So the fact that we can deliver burst and an SSD performance at that price point and in the ability to do it easily, we think it's important, so that's why we're putting it in front of you. That's why we're making it the first choice. We've changed the pricing of GP2. So GP2 is priced on, I think it's 10 cents per gigabyte per month. We don't have any IOPS charge in there. It's very simple for you if you're designing an application to work out what will it cost for 100 gigabytes of storage inside my application. It makes it much easier for you to architect for cost as well within the platform. So takeaway here, always use GP2 for root volumes. So if you have got volumes or AMIs you made yourself, so you've created your own custom AMIs and you're running those within your workload, there's a good chance if you created them before the middle of last year or haven't looked at how your AMIs are being created with Packer or other tools like that, that volume's probably magnetic because it's the default choice. And all you need to do is update the block device mapping, and that will then enable the access to GP2. How do you migrate onto GP2 data volumes? So if you've got data volumes and you want to just move that data over, you can easily change the type when you're launching. So if you're launching a new application that's using a snapshot, you can change it from magnetic to GP2. You can use EBS snapshots, which we'll talk about a little bit more, to move the data easily to new volume types. So when you create a snapshot, that snapshot can easily be recreated as any volume type. So you can actually use it the other way around as well, a little tip. If you're moving data onto nearline, if you're moving it to magnetic, you can take a snapshot and then run it back on magnetic and lower the cost of running it. Some file systems support resizing, so you'll be able to resize your volumes if you previously over-provisioned your volumes because you needed more throughput or you needed more capability of IOPS. You'll be able to resize those volumes to save some cost on there. So why do we have, what are the benefits, or why do we have EBS snapshots? Well, the first thing is they're more durable than EBS. So EBS is already very durable. It's replicated data within the availability zone. There's multiple copies of your data when you do a write into EBS. But if you want even more durability or the ability to take data and maybe move it to another region for disaster recovery reasons, if you make an EBS snapshot, we store that in S3. And once it's stored in S3, you can then copy that snapshot to another region. You can share it with another account. You can do a lot of really cool things with EBS snapshots. They're differential. So they're not a typical snapshot in the sense that when we take a snapshot of an EBS volume, the first time we do it, we take a copy of the whole volume. So a 100 gigabyte volume, we'll take 100 gigabytes and we store that as your snapshot. The next time you take a snapshot, we will only take the data that's changed. So it's an incremental or a differential backup of your volume. So if you've only changed 10 gigabytes of data since the last snapshot, and you use an EBS snapshot, we'll back up 10 gigabytes. Now, where it gets really interesting is we're intelligent enough in the EBS service to understand exactly where all of those blocks are, who's changed them, which bit is dirty. So you can make one EBS snapshot when you create the volume. You can then make 4 snapshots subsequently over the day or over the week. And if you delete any of those snapshots, we'll still have a full snapshot because we keep all of the blocks that are dirty, and we keep track of them. So you don't need to actually keep all of your snapshots. You can actually keep one snapshot and then one daily as you move through. They're independent of the availability zone, so it makes it easy for you to move volumes around. If you need to get data from one availability zone to another, an EBS snapshot is a great way to do it. And of course, you can copy them over the regions. Hopefully you've already learned this if you've been working with AWS for some time. If you're not, I plead with you, please tag everything. Okay? Everything supports tags. I can't think of many things that don't support tags today. Tag everything. Tagging enables you to then easily go into your infrastructure, both in EBS and snapshots, as we're talking about here, but also in EC2 and other parts of the service, and identify systems easily and quickly. You could see what the purpose is, its production, its dev test, you know, who's launched it, what cost center it is, if that's one of the aspects that's important to you. So use tags and tag as much as you can. And when it comes to snapshots, if you use tags, it's very easy to filter using the CLI or the console and pull out all of my snapshots for a particular instance or all of my snapshots for a particular volume. And then easily you can modify those, copy those, or throw them away if you don't need them anymore. So that's the overview of EBS. I'm going to move now into talking about the performance and diving into how do you choose the right EC2 instance, how do you size your volume appropriately, and what are the aspects of EBS that are going to deliver the performance you're looking for. So I need to start out with a little bit of theory. It's kind of important because this is actually what tuning theory is based in. So Little's law, which is the queue length multiplied by the arrival rate multiplied by the wait time. So in EBS speak, that is the queue depth multiplied by the IOPS multiplied by the latency. Now, this is a fundamental law that applies to all storage tuning. This is not something that's unique to EBS or something that we're driving you to learn. This is how you would optimize and tune a typical storage solution on-premise. And so these same things apply on-prem as they apply on AWS. And so it's good to understand this foundational theory. When we think about performance, we typically think about three things. We think about the amount of IOPS that are being achieved or the amount of IOPS that we would like to achieve. We look at the latency. How long is it taking for those IOPS to actually move around in the system? And then the throughput. How much data is being moved backwards and forwards? And typically, when we talk about performance, we also have performance goals. So there may be some goals you're trying to achieve. You may want to be moving 2,000 IOPS. You may want to have 200 megabytes a second of throughput. And so we need to understand how to measure and observe those when we build the platform. So there's 4 key components that we're going to talk about and how they impact performance on EBS. We start with the EC2 instance. And it's important to select the right EC2 instance. We'll work our way through that. We then have the actual I/O that you're doing, so sequential or random, 4K or 32K or 1 megabyte. So the I/O that you're sending, the actual workload down to the system. The network link, because as I mentioned, EBS is network-attached block storage. So there's a network link from the EC2 instance to the EBS server that's providing your volumes. And it's important to understand that you have choices there, and that will impact your performance. And then we have the EBS, or the EBS volume itself. What size of volume do you have, and what type of characteristics does it have? So we've got 6 areas we're going to dig into specifically and highlight how you would design for performance, how you would appropriately select the right features to get the most out of EBS and EC2. EC2 instance, the EBS-optimized instances, workload, queue depth, RAID. RAID's still an important aspect if you're looking for particular performance characteristics. And then pre-warming, the dreaded pre-warming. So the EC2 instance. So we offer a lot of instances. Andy covered in the keynote this morning the large selection of EC2 instances and all of their capabilities. All of them have different characteristics. And so when you're choosing an EC2 instance, you're typically looking for a particular CPU profile or a certain amount of memory that it needs to have. Or maybe it's a general purpose. It's a web server. And so those memory and CPU balances make sense. But when you select them, you also need to be aware that all of them come with a particular amount of network capacity as well. And so if you grab a T2 micro instance and you attach a 4,000 IOPS provisioned IOPS volume to that instance, it's not likely that you're going to be able to drive that performance from a T2 micro. They're just not sized appropriately, okay? And so you need to make sure that you're choosing the right instance for the amount of storage I/O that you want to drive in the platform. Once you've chosen the right instance for your application, so you've selected your M3 or your C4, you need to make sure that you're actually turning on some of the attributes in that instance that make it effective or able to drive more performance in EBS. And because these are choices, they're not on by default except in some of our newer instances like the C4. So EBS-optimized will give you an amount of bandwidth between your EC2 instance and the EBS server, and you can choose 500 megabytes, 500 megabit, 1,000 megabit, 2,000 megabit, 4,000 megabit of EBS optimization, which gives you a different path for EBS traffic than your regular instance traffic. Now, where this is really important is if you've architected your application, you've set it all up, it's running on a M3 2 extra large, and you're driving lots of traffic to it. You've got lots of users coming in, accessing your application, or people are connecting to your database. If you don't have EBS optimization turned on, what you're actually doing is you're contending traffic on that network link. So they're having to share the same network link as the EBS traffic. And so you're going to get inconsistent performance. So if you want to have consistent performance, you need to make sure EBS has got its own bandwidth so it's not fighting with other traffic on your network. The 10 gigabit instances, so our ATXL instances, they actually have 10 gigabit all the way to EBS as well. And so with those instances, you can work out whether that's the most appropriate for driving a lot of storage performance. Enables you to drive up to 48,000 IOPS on those instances, or all the way up to 800 megabytes a second. So takeaway here, please use EBS optimized if you want consistent performance. So if you're benchmarking or developing your application, you're not sure whether the performance is coming from network traffic from your users or somewhere else, make sure EBS optimized flag is on so you can separate that traffic out. Understanding your workload is going to be really important when you're sizing EBS or when you're selecting the right EBS volumes. So as I mentioned, we measure up to 256 kilobytes as an I/O. So it's slightly less important than it used to be to actually size appropriately, because IOPS used to be 16K, and so if you were driving a 64K workload, you needed to effectively double or quadruple the number of IOPS that you wanted so you could drive that through the platform. Read and write workloads actually don't make that much difference on EBS. It's one of the interesting characteristics of it being a service. So unlike your typical hard drive where read and write are typically different performance levels, they're the same on EBS. But it's good to understand how they perform exactly. Your I/O pattern is important. So are you driving sequential I/O or are you driving random I/O? So if you're driving sequential I/O, even if you're driving 4K sequential I/O, we're going to see that as sequential I/O and do our best to really translate that all into 256K I/Os. And you'll be able to drive a significant amount of throughput through the volume with hardly any IOPS being used. But if it's all random, then it's all going to be IOP driven, and it won't matter about the throughput. You're going to quickly exceed all the IOPS on it. And then I/O concurrency. So I/O concurrency is something you typically can't easily manage inside your application, but it's something you should be aware of. So if we're benchmarking, if I was using a tool like FIO, I could set QDepth to 4 or QDepth to 8, and that will actually manage the number of IOs that are pending for the block device, and I can easily manage and measure that. Within an application, I/O concurrency typically means how many threads are doing I/O to the volume at the same time, how many processes are running inside my web server or inside my database. And so at a certain point, too much I/O concurrency will increase your queue depth and it will have a negative impact on your performance. So it's important to understand that. So when we talk about limits on EBS, it's important to understand that the two are separate, although they are joined because throughput is IOPS measured by the amount of I/O size. An EBS volume, or provisioned IOPS EBS volume, can be provisioned up to 20,000 IOPS. And it has throughput up to 320 megabytes a second. However, it doesn't mean you can do both of them or all of them at the same time. So if we take an example here of an 8,000 provisioned IOPS volume, we can definitely drive 8,000 8K IOPS. We can drive 8,000 16K IOPS. What we cannot do is drive 16,000 IOPS because that's more than the provisioned IOPS of the volume, even though throughput-wise, all of these are under 320 megabytes a second. We're exceeding the provisioned IOPS capability. In the inverse, when I take a look at throughput on this volume, we can definitely drive, I can't drive 8,064K IOPS. It's 512 megabytes a second. And so therefore, that's exceeding the 320. So I can drive, though, 1,250 at 256. And so that's the difference between sequential and random on the workloads. The more sequential it is, typically you're not even going to exceed all of your IOPS. What's important to understand is if you were really building a throughput application here, you wouldn't need 4,000 IOPS in that EBS volume. You could probably do it with 1,500, maybe 2,000 if you're a little bit conservative. And you're only paying for the provisioned IOPS. The throughput is an aspect of it afterwards. So the block size is going to determine how much throughput you can get from your application. So it's important to understand what is the size of IOs I'm sending down to the volumes and how are they being measured as we go through. So queue depth is an important aspect. Because it's network-attached block storage, now queue depth appears also in local storage, but with network-attached storage, once the I/O is gone, it's off into the queue, there's nothing I can do. So it's important to make sure I'm feeding that queue, feeding the network pipe appropriately, and keeping it filled and driven hard enough to get the performance I'm looking for. You can monitor it with CloudWatch. And so these CloudWatch metrics are important. If you haven't dug into CloudWatch metrics for EBS, they measure all of the aspects of the volume that you would need to actually work out things like queue depth and latency and throughput and arrival rate. So you can apply Little's law to your queuing tuning, or your tuning theory, and understand whether you're actually getting what you expect from the volumes. So talk a little bit about what an I/O latency is and how we can improve I/O latency. So I/O latency is the amount of time it takes for an I/O between submission to the block device and the completion time as far as the application is concerned. And what I want to do is talk a little bit around how we measure and think about IOPS. So this is a really, really messy graph. This is a heat graph, and you can see that our read IOPS are red and our write IOPS are blue. And they're all over the place. And it's very hard to understand what's going on in that graph. So what I want to do is introduce, before I go a little bit further, for folks who don't remember this, what a box plot is and how we use box plots to understand this, and then show you the impacts of different choices around I/O latency for EBS. So in this box graph, I'm going to show you the same graph we just did, but it breaks it down so I can take a look at the median, what is the average going through the platform. I can then take a look at what's called the P25 and the P75, so the 75 percentile and the 25 percentile. And then I also have the top and bottom of the data, what was the 0 and the 100. So let me show you a baseline latency. This is some latency testing done on I/O, on an instance with, I think, random IOPS. And we're doing an M2 4 extra large on magnetic. And so you can see that roughly the median is sitting logarithmically. We're probably sitting around 5 milliseconds there. I've got some pretty big outliers pushing all the way up into between 10 and 100, and it comes down pretty low, but not too far. So the first change I make to this platform, if I want to reduce the latency, if I want to get my EBS performance better, is I'm going to move it over to GP2. So you can see with the introduction of GP2, so the plot that's on the right-hand side to you, my median has significantly come down. So on average, most of the IOs are coming in around 1 millisecond. That's really good. But I do have quite a lot of I/O that's falling outside of the median. I've got quite a big box still there. So that shows me there's still a lot of variability in the I/O that's passing through. Although my medians come down, there's still a lot of I/O variability. However, if I change it to an R3 2XL, which is the latest generation but equivalent of the M2 2XL, you can see that my median's now dropped under the 1 millisecond. I've got almost no outliers in the 25 to 75 range, and a couple who sort of take me up a little bit, but most of them come down. And so now I get a really consistent latency profile by making that change. But the really cool thing about making that change is it's cheaper. So the GP2 is cheaper, and the instance is cheaper. So if I move from an M2 2XL to an R3 2XL, I'll actually spend less, get better performance, and lower latency I/O. So I want to try and spend a little bit of time explaining how queue depth impacts your latency within the EBS platform. So what we're graphing here is the TP90, so the 90 percentile of latency. So most of them complete within 90. And it shows you the queue depth along the x-axis and the latency in milliseconds. And so this is for a 4,000K provisioned IOPS volume. And you can see that it starts out with a queue depth of 0.075 milliseconds. And as we increase our queue depth, it starts to go up. If we graph over the top of it the number of IOPS achieved against the latency, you can see that when we have a queue depth of 1, I'm only achieving 1,800 IOPS. So I've provisioned a 4K volume, but I'm not getting the IOPS I'm looking for. So this is one of the aspects of EBS that you need to understand, is if you don't have enough I/O in the network pipe, if there's not enough IOPS going down to the EBS volume, you're not driving it hard enough. So you might have a 4K volume, but if you're only sending IOs with basically one pending and nothing else, it's not going to drive it hard enough. So what we do see is if we increase our queue depth and we head up to an optimal queue depth of around 4 typically, that we're going to be able to drive 4,000 IOPS comfortably. But we're still in the single-digit millisecond latency. So it's only 2 millisecond latency for the writes. Of course, if we were to take it all the way up to the other end, you can see that if your queue depth is too high, it impacts your latency substantially. It's taking over 35 milliseconds for these IOs to return back to the application. Now, this is when I was talking about IO concurrency. So if you've got too many threads doing IO on a volume, you're going to drive up the queue depth. And when the queue depth reaches a certain point, your I/O is actually impacted substantially. And just to make sure we highlight this, this is the write latency. And you can see that, again, it's the same numbers roughly for write latency as it is for read latency. So some takeaways when we talk about latency and performance. Use the SSD volumes with the latest EC2 instances. They're probably cheaper, and they're probably faster than what you have today. So it really behooves you to go out and actually make those changes. And the optimal queue depth you're looking for, so queue depth is important as we drive this workload. The optimal queue depth is going to be typically between 4 and 8. We use a number of about 1 to 500 IOPS. The larger your queue depth gets, it may not be optimal. So if your number comes out at like a queue depth of 30, then you might want to dial it back down a little bit. But typically 4 to 8 is where we start out. And EBS-optimized instances provide a consistent latency experience. So if you're doing a lot of work around EBS, if EBS is actually one of the key components in your application architecture, please make sure you're using optimized instances. So another aspect we have for increasing or driving more performance is RAID. Now, with the introduction of larger and faster, it's now possible to attach up to 16 terabytes of EBS to an instance, and up to 10,000 IOPS and 160 megabytes a second if you're using GP2 or general purpose, or 20,000 IOPS and 320 megabytes a second if you're using provisioned IOPS. Now, those are pretty big numbers. 16 terabytes of storage is a lot of storage in one volume, and those throughput numbers are pretty substantial as well. But there may be a time where you need more. Typically, we see it in a throughput type application where someone wants to drive maybe 500, 600 megabytes of I/O through to GP2. You're still going to want to put them together in a RAID configuration. So when you take a look at RAID, you typically want to be looking at something with RAID striping. There's no value in doing a RAID 5 or a RAID 6 on top of EBS. The software has already replicated, or the service has already replicated your data within the availability zone. We've got 5 nines of availability. The annual failure rate is, I forget the exact number, 0.0 something, 1 to 2. It's an extremely low failure rate. It's more durable than a hard drive by a long way. So RAID 5 is not going to help. So the only RAID configuration that's typically worth investigating is for more throughput and more performance, and that's RAID 0. This is just some testing I wanted to share with you we did to show that you can actually drive some pretty crazy numbers through an EC2 instance. So this is an 8XL instance, one of the 10 gigabyte instances or 10 gigabit instances. We're driving up to 48,000 IOPS through the EBS volumes, and it's going up to 823 megabytes a second. So you can drive a huge amount of I/O from one of the large instances down to EBS. If you are doing RAID, once you've RAIDed those volumes together, typically the stripe size that makes the most sense as a takeaway for you is 128K or 256. Anything under that, you're probably going to end up having all the I/O merging happening anyway, so it doesn't really make sense to do anything less than that. The dreaded pre-warming, I do have to talk about it just for a little bit. So pre-warming is an aspect that comes up typically when you're benchmarking EBS. So there's something called the first access penalty today in EBS. So when you first touch a block, it's going to have a slightly higher latency than the second time or the millions of other times you touch that block in the lifetime of the volume. If you're doing benchmarking because you're trying to qualify an application on top of an EBS volume or a particular configuration, you may need to pre-warm. And there's documentation that explains it, and it's something that we're always working on to reduce the impact of. But you may need to do it, so pay attention to the documentation if you're benchmarking. If you are going to pre-warm a volume, use a very large block size. Please don't go in and pre-warm the volume with a 4K because all you're doing is testing IOPS. You really want to send like 1 megabyte or 2 megabyte IOs down to the volume. Some final tips around performance for that. These larger and faster volumes have some interesting side effects that you don't realize. So when you're formatting 16 terabytes, it takes longer than formatting 100 gigabytes. And so make sure you're using file systems that support really fast initialization. So in the Linux space, things like ext4 and XFS are going to initialize substantially quicker on top of that block storage than if you're using ext3 and other file systems. And alignment does matter. So we present a raw block device to you. You should be using 4K alignment. Older operating systems, so the RHEL 5 family, some of the older Windows stuff, they don't recognize that we do 4K sectors or 4K alignment in EBS. And so you can actually impact performance by doing that. So if you're truly looking for performance, make sure you choose the right alignment sector size inside EBS. There's another cheat sheet for folks who want to take a quick picture, but we'll put them up on slides here. This is really to help you understand where we think some of the performance numbers look for different applications or different databases and workloads on top of AWS. The numbers you should be able to achieve in the most optimal configuration. So if you followed all of the tuning advice, you're using EBS optimization, you right-sized your instance, you've got the right size of EBS volumes, your queue depth is appropriate, we think you should be able to drive these numbers happily. So if you've done everything correct, what you should end up with is something that looks like this. And it's an interesting graphic, but what we're trying to take away here is that if everything's right-sized, if your EC2 instance has got 1,000 megabit per second of EBS optimization, and your application is tuned appropriately to drive on top of that, and you've got the right volume or volumes configured, you should have a well-balanced system and be able to drive performance end-to-end through that platform. So just to recap, the tools you have available for tuning performance on EBS and EC2, you have the EC2 instance, right-sizing the EC2 instance. You have EBS optimization. You have your workload, so making sure you understand that and tuning your workload appropriately. Make sure you have the right I/O concurrency or you're using the right block size. The queue depth. You have RAID if you need more performance than we offer today with larger and faster. And then you do have pre-warming if you're doing benchmarking. Now I want to take a little bit of time and talk about encryption. Encryption is an important aspect of EBS, which I think we've made substantially easier at reInvent, and I want to just kind of refresh if you haven't seen this already. So why do you want to encrypt data volumes? So typically people are encrypting because they have compliance or security reasons within their business. They need to make sure that they're securing data so they can pass that sort of assurance onto their customers or onto their CISO that they're carrying this out. And so when you encrypt data volumes, you need to come up with an infrastructure to manage it. You need to come up with a way of managing the encryption keys and managing the services with them. And so we used to have the options of third-party products like Symantec and Trust and Trend Micro. And now, with the introduction of KMS, which if you haven't seen it before, we launched at reInvent, we now have an AWS native key management service. Now, key management is not a very fun topic. A good friend of mine, our security solution architect, says it's very boring to talk about because it does exactly what it's supposed to do, nothing more, nothing less. It secures your keys with an auditable trail and exposes them to services so they can use them when they want to access your data. It's very boring, but it's very easy to use inside AWS today. So you can create a key, you can associate a key with projects, with workloads, with customers, any particular reason you want to create a specific key. And then you can pass that key into our services, and we'll use that key to encrypt your volumes. Now, what's really cool about EBS encryption is it happens on the EC2 host. So when you choose an EBS encrypted volume, you say, hey, encrypt that volume for me. We're going to encrypt the volume on the EC2 host where your EC2 instance is running, and then all of the data that's passing backwards and forwards over the network link, that's encrypted with your key. And then the EBS snapshot that you're going to make with it, because you do snapshots regularly, that's going to be encrypted as well. So all of your data is going to be encrypted. So it's going to be encrypted at rest, and it's going to be encrypted in flight as it passes through the network. And that's a really cool feature, I think, of EBS. It's also super easy to do. Okay, when you go to create volume in the console, you can just turn on a flag encrypted if that's the only thing you have to do. If you want to use KMS and manage all of the keys that go with it, you just enter the key, and we'll use that key when we create the volume. This is a deeper dive into how it works. I will happily take questions on this because I'm starting to run out of time. But the encryption keys uses a concept of wrapper keys, and we can do a sideline on exactly how KMS encrypts. So a summary, when you're trying to get performance, when you're really architecting for performance on EC2 and EBS, you want to make sure you select the right volume for your workload. So that might be general purpose because you have a general purpose workload. It might be provisioned IOPS for that really high performance database. Or it might be magnetic because you've got cold storage that you want to keep online or cold data that you want to keep online. Get the right instance. So if you haven't recently refreshed your instances you're using, make sure you're using the latest generation instance. Make sure you're turning on attributes that make a difference, provisioned IOPS, EBS optimization, for example. Take snapshots often, take snapshots early. The thing about snapshots is they're not very helpful when you have a problem and you want to go back in time if you haven't made them, okay? So make a snapshot when you create the volume, okay? They don't cost a lot, so make a snapshot when you create the volume, and then later on, it's very easy to make a new snapshot and only get the differential data. And leverage encryption if you need it. If encryption is an important aspect of your workload, please use it. It's very easy to turn on, and it's very easy to audit. And with that, I will happily take Q&A. We have a mic there if folks want a mic. Otherwise, I can relay questions. I'm going to start with you, sir, because I asked you to wait.
The question was, when you talk about IOPS, you talk about after whatever level of service is using to create its own level of redundancy?
OK, so the question was, when we talk about IOPS, are we talking about IOPS that are provided or after the service has created the volume? So when we talk about IOPS, we talk about the IOPS you can achieve in that volume. So any of the work we do to make sure your data is durable and redundant within the availability zone has nothing to do with the IOPS we deliver to you. 100% usable IOPS. So if you provision a volume with 2,000 IOPS, it has 2,000 IOPS you can use on your instance.
Two questions. One is, you mentioned that you can control how much EBS optimization is being used. I haven't seen that. I either see turn EBS optimization on, and that's it.
Yeah, so the question was, I mentioned that you could choose the amount of EBS optimization you want to use. And so that's basically an attribute of the instance. So for example, certain instances have different levels of EBS optimization. So if you choose an instance like an M3 large, it has 500 megabits of EBS optimization. M3 extra large has 1,000 megabits. And so each instance. An R32XL, I think, has 1,000 megabits a second, but don't quote me on that. It could be 2,000. So the question was if you go up to higher instances. So an 8 extra large instance will have either 10 gigabits of EBS optimization, but on the latest one, the C4, or if you're looking at the previous generations, like the C3s and the CR1s and stuff, they have a 10 gigabit to everything, so they can choose how much bandwidth they drive.
My other question is, you mentioned RAID stripe size.
Mm-hmm.
Is that just when you're configuring your volumes within your OS?
Yes.
Yeah,
so the question was, when I mentioned RAID stripe size, I suggested 128 or 256. So that's really when you're creating the RAID volume within the operating system, so within Linux or within Windows. Yeah. No, so when you match what you're doing there when you match it to SQL Server is you're basically causing all of the I/O to never be merged. We'll do our best to merge it on the back end, but at your OS, you're actually adding overhead. So the block size should actually match the 128, 256. Yes.
About Cassandra use case, you had it in one slide. So some people recommended against using Cassandra with using block storage, using only ephemeral storage. So if the GP2 doesn't make sense to use Cassandra?
It does, yeah. So we have lots of customers. So the question was, you mentioned Cassandra in the slides, and some people recommend using ephemeral with Cassandra. And so there's going to be different use cases for different customers. So if we take a look at our i2 8XL, which is our really high IOPS instance, that's going to drive a very large number of IOPS and throughput. And if you have a very extreme Cassandra workload, that might be the instance that you're looking for. But what we typically find is that customers are not actually at those numbers for performance. They're much lower. And GP2 provides those numbers with the additional benefits of increased durability and easier snapshot and management of the application. So it might not make sense when you look at it, but when you start to look at the total cost of ownership, so what does it cost to look after my instances and manage them? And so with Cassandra on ephemeral, if one dies, you need to remirror or remaster him in from a new instance. With EC2 and EBS for Cassandra, if something happens to the instance, we'll auto-recover it now. You can turn that on as an option. It'll just come right back up with the volumes attached. They're already there. So the recovery time is significantly shorter. Yes?
I've created an encrypted volume before, but I found that when I tried to attach it to an instance, the instance didn't show up as available. Do I need to have a special instance type, or why wouldn't it appear?
Yes, so the question was, I've created an encrypted volume, but I couldn't attach it to a certain instance. So only the latest generation instances support encryption. And the reason for that is because we leverage the Intel AES extensions in the CPU to offload encryption so that we can do encryption at the least cost to your application environment. So if you've created an encrypted volume and try and attach it to like an M1 or a T2, then it's not going to be available. So in the EBS encryption details, it lists all the instances that support encryption.
So I should be able to attach it to an R3 large, though, right?
Yes. Okay. It's not that bad. At the end of the day, encryption is never free. There's always going to be some cost to it, and I'm happy to talk about it offline about the exact use case. Oh, you mean key? Well, the way KMS works, it's got master keys. So when you're doing key rotation, it doesn't change the actual key on the volume itself. So we have questions on the mic. I do apologize.
So you talked about let's say contention between the network traffic and the EBS traffic. Can you talk about that? And what does EBS optimized give you?
Sure. So when I talk about contention, I don't talk about contention that we have, but more that the contention your application may introduce. So if you have a lot of connections, maybe you're a web server, there's a lot of requests coming into your web server, that network pipe is going to be then sharing itself with EBS traffic. What EBS optimization does for you is carve out bandwidth separate from the instance just for EBS. And so you get this consistent performance throughput to EBS. Next question.
What's the performance penalty using encryption?
The performance penalty using encryption, it depends on the specific workload, block sizes, IOPS, et cetera. I'm happy to chat to you about what your workload is.
I have a quick question. Under Linux, what would you recommend for your RAID? I noticed you had up there either soft RAID 0 or LVM. What would you recommend to actually balance it so that you don't get a hot disk?
So typically MD-ADM on 0 is going to balance your IOs anyway. It does a balance over them. With LVM, you want to make sure you're doing LVM stripe and not LVM linear. So a lot of people get caught out with this. There's some great blog posts from lots of people around this. I've been burnt by it myself in the past. But when you do LVM create, I think it defaults to linear, which means fill up volume 1, then volume 2, then volume 3. So that's what you end up with this hotspot feeling, because you're like, hey, I should have twice the performance because I have 2 volumes. So watch out if you're using LVM that it's doing a proper stripe and not doing linear. Cool. We're officially out of time at this point. So unless there's any burning questions, thank you very much for coming today.